Today we're on page 4 of the Chemistry 1 Chapter 8 packet, and we're going to be discussing covalent bonding. Covalent bonding is different than ionic bonding. We already talked about ionic, where you have a metal and a nonmetal. This is going to be two nonmetals, and what they're going to do is they're going to share electrons, whereas with a metal and a nonmetal, the metal lost and the nonmetal gained. We're going to start talking about methane, which is CH4. Methane is natural gas. That's what's going to come out of your stove if you have a gas stove at home. Also might be used to fuel your water heater, your dryer. Any of these things can use natural gas. And we also use it in class when we do our Bunsen burners, and that's how we get this blue flame in class as well. So methane is CH4. It's got one C, and it's got four H's. So the four H's are going to go together around the C, and we're going to see how that works. So we'll start with writing the electron configuration for the valence electrons. We know that C has a 2s2 and a 2p2. Now there's a little bit of a problem with this, because if this is really how C arranges its electrons, then the Lewis structure would be something like this. And so you would only really be able to make two bonds. You could only really share this electron and this electron, and that wouldn't really be contributing to a higher stability, because the carbon would only have 6 electrons altogether. 1, 2, 3, 4, 5, 6 in the valence, and that's not good. It wants to have 8. So sharing 2 is not good. Plus, we actually find out that carbon has 4 bonds whenever it bonds with something. So we see that carbon must do something differently than we expected, and it does. What it does is it promotes an electron. It takes this electron right here and promotes it. We've seen that happen before with chromium and copper in the last chapter, where they also promote the electron as well. So carbon does not have a 2s2, 2p2. It actually has a 2s1 and 2p3. So when you draw the Lewis structure for carbon, it's going to be something like this. Carbon is going to have 4 dots. 1, 2, 3, 4. Now we know that we have 4 H's, and each H has 1 electron as well. So we'll draw each H like this. 1, 2, 3, 4. And what you do with covalent bonding is connect the single dots to make a bond. So you could see that the C can connect to the H 4 times, 4 different H's, and that's going to be your drawing. So if we drew the final copy, technically, you really shouldn't show those dots for the bonds. So this is the final copy right here for methane. Okay, so what you're going to see you could draw here is you could draw another 1s for each H. So there are 4 H's. They each have a 1s1. And what you're going to do is you're going to share between the electrons. Okay, so these are going to share. This one is going to share here. This is going to share here. This one's going to share. And this one's going to share. And so you have 4 shares going on for the carbon between the 4 hydrogens. All right, so we know the name of this is going to be methane. And we could easily find the electronegativity difference by looking at page 2 in the packet. And when you look up C, it is 2.5. And H is 2.1. So when you subtract those, you get a difference of 0.4. And you'll notice right away that 0.4 is a much smaller number of a difference than we used to have with the ionic. The ionics were much higher numbers than this. So it goes to show you that there's a small difference in electronegativity between nonmetals as opposed to a metal and a nonmetal. Okay, let's go to this one with H and Cl. So H is just a 1s1. Cl is a 3s2 in the valence and a 3p5. So that's going to look like this. And we could see what's going to happen here very nicely. This H could share with this 3pz orbital. And if we draw this out, we'll see that H has 1 electron and Cl has 7. Now we didn't address this in the last example with the hydrogen. You'll notice that hydrogen only in the last example is going to have 2 electrons, 1, 2, because they share. Now hydrogen can be stable with that because it only wants to have 2 to fill its 1s, and it'll be like helium, which is a noble gas. So the same thing happens with this hydrogen. It only really wants to have 2, whereas that chlorine wants to have 8. 8 is called the octet rule. All right, I'll just write that here. The octet rule tells you that every element wants to have 8 valence electrons, except hydrogen won't want to do that. Now again, technically you shouldn't show the dots in the final structure of the bond. So technically you should go like this, and this is your final answer. Now the name of this, we understood that this is an acid, but that's only going to be true if it's aqueous, if it's dissolved in water. So if it's dissolved in water, this would be called hydrochloric acid, as we learned earlier in the year. However, if it's a gas, which it can be, you would just name it as hydrogen chloride. You would not name it as an acid unless it were actually aqueous. And then to get the electronegativity difference, the Cl is 3.0. We said that H was 2.1. So when you subtract these, you get 0.9. Again, a fairly low number in electronegativity difference. Okay, let's move up to the next one on the next page. Next example on page 5, we're going to draw phosphorus with a 3s2 3p3 for the valence, and fluorine with a 2s2 2p5 for the valence. So you could see that phosphorus would like to share 3 electrons. However, fluorine can only share 1 electron. So if this fluorine shares with this phosphorus electron, it's finished, but the phosphorus is not finished. So that's why we're going to need 3 of the fluorines to bond with the phosphorus. So if we fill this in, we could see that this electron could be shared with this electron, and this electron could be shared with that electron. And when we draw the Lewis structure, we're going to draw a P with 5 valence electrons, 1, 2, 3, 4, 5. And then every fluorine is going to have 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4, 5, 6, 7. And we're going to share with the single electrons like that. And technically, again, you're really not supposed to show those dots in the lines when you're done. So we just redraw it neatly like this. And here is our final structure of PF3. We could name this as a molecular with prefixes. So phosphorus trifluoride. Remember to spell fluoride correctly. And the electronegativity difference, F is a 4.0, and phosphorus is a 2.2. So this one comes out to be a 1.8, which is a little bit higher than the other electronegativity differences that we had before for moleculars, but generally still on the low side. Okay, we'll move on to the next example, which is C and O. And it's CO2 that we're going to do. So remember what we said about carbon. Instead of being a 2s2, it moves one up into the 2p, so it has 4 single electrons. And the oxygen does a 2s2 and then a 2p4. So it has 2 electrons to share. So you could see that we could share right here, and we could share right here. But then the carbon still wants to share, and the oxygen is already done, so we need another oxygen to share. And then this is going to share right here. This is going to share right here. Of course, this is a big mess, but it's just to get the point across that they share twice. So here's the carbon with 4 single electrons. Here's the oxygen with 6 single valence electrons. Not single, but 6. And then what we do is we connect. Now I kind of set this up ahead of time so I could line it up nice and neat, like this and like this. Okay? On your rough copy, if you didn't happen to line it up like I did, and let's say you lined it up like that, and let's say you lined it up like that, and then you wanted to connect it, and you went like this, and then you went like this, and then you went like that, and then you went like that, that's fine for a rough copy. It doesn't matter. It just helps you to see what the final copy is going to look like. You're never going to hand in the rough copy as your final answer. You're going to go like this at the end, put a double bond between each O and the C like that, and this is going to be your final answer. When you name this, you know you use prefixes, so this is going to be carbon dioxide, and the electronegativity difference, O is 3.5, and carbon is 2.5, so this is a difference of 1.0. On this page, we're just going to draw the Lewis structures without showing all the orbitals of the S's and the P's, but we are still going to stick to the rough copy, final copy method here. So CCl4, you see that the Cl has 7 and the C has 4, so that gives you a clue how they're going to bond just with their single electrons. So we're going to connect the single, connect the single, connect the single, connect the single, and then we draw a rough copy, because technically you're not supposed to show those dots in the bonds because the line represents the two dots. So you can just draw the final copy like this, and you have your CCl4 drawing of the Lewis structure. Now, Cn minus, we recognize this as cyanide, one of our polyatomic ions. And now we're going to understand, why does cyanide like to be -1, not -2 or -3 or +1? So we're just going to draw the C with 4 dots, 1, 2, 3, 4. We're going to draw the N with 5 dots, 1, 2, 3, 4, 5. You're going to notice that when I do my drawings, I try to keep the single electrons between the two atoms because those are the ones that are going to connect. You know, if you don't, then it's just going to be a little messier in the rough copy, but it won't matter in the end. And we have an extra electron for this minus sign. I'm going to save that to the end to see where I need it. So I'm going to connect the C and the N as many times as possible with the single. So I can connect once, but I still need to connect more because you can't leave single electrons by themselves. So we're going to connect 3 times. And now you could see that the cyanide would like to have one more electron on the C, like that. You draw brackets with a minus sign to show that there's an extra electron in your drawing. Because, remember, I personally do the X's, but you could do a dot here. So if you had all dots, you wouldn't necessarily know you had an extra electron, so that's why I do the bracket and a minus to show the reader that you have an extra electron. So when you draw the final copy, you're just going to draw a triple bond between the C and the N. You have a pair on the N, you have the extra electron on the C, and then you go -1 outside like that. Okay, now we're going to draw CH3OH. You've probably seen formulas like this before. This is methanol. We did a demonstration on this in class with combustion. And you might wonder, well, why do we put this H by itself, and why don't we just say CH4O? Even though CH4O is mathematically correct, it's not structurally correct. So it's helpful in chemistry to show the structure of a molecule by the formula. So this means that you have a C with 3 H's around it, and then you have an O, and then you have an H. Now draw all your dots for the valence electrons. The C has 4, each H has 1, the O has 6, 1, 2, 3, 4. Again, I'm going to keep the singles between the atoms, 5, 6. So now you're just going to connect all the singles, connect, 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 and there's your drawing of methanol. If you want to draw your final copy without showing the dots in the lines, you simply draw this, and you do need to remember these lone pairs on the oxygen like that. Okay, so far these are just a straightforward covalent bonding. Of course, you know there are going to be exceptions and things that are different, so we're going to get into that right now. Here's CO. You know that this is called carbon monoxide, and you know carbon monoxide exists because you've heard of it before. It's actually a very poisonous gas. You don't want to breathe that in. And we're going to draw the Lewis structure for carbon monoxide. So C has 1, 2, 3, 4 valence electrons. O has 1, 2, 3, 4, 5, 6. So we're going to connect the singles as much as possible. We're going to connect one there, we're going to connect one here, and now we are stuck. Because C does not have 8 electrons, it's not satisfying the octet rule. It has 2 missing on here. O is satisfied with the octet rule, but C is not. And there are no extra electrons that we can use. So what we're going to do is called a coordinate covalent bond. A coordinate covalent bond is going to occur like this. You're going to have this electron is going to move over somewhere else to pair up with that one. And then the O is going to donate this pair as the bond. Okay, so let's talk about that. Usually in a covalent bond, one atom shares one atom shares one. Okay, so it's like I share one, you share one. I share one, you share one. All right? But now this is moving over, so the O is basically donating both. Okay? So it's carbon shares none and the oxygen shares two. So I share two, you share none kind of thing. So when you draw this at the end, you're going to have a C and an O. The O and the C are going to have a triple bond. Now you could draw the triple bond like that with the arrow, that's fine, and then the lone pair on the O and the lone pair on the C. Or you could just draw it as 3 lines, which the book will often do, and that's going to be the same thing. Okay, so you don't have to show the arrow, but it's important to understand that this does have a coordinate covalent bond because one shared both. Okay, let's try SO3. So here's S. We have an O and an O and an O. So S has 6 valence electrons. O also has 6 valence electrons. And this O has 6 valence electrons. And this O has 6 valence electrons. So we're going to try to connect the singles. So I could connect here, and I could try connecting here, but now I'm really going to be stuck. So the first thing I want to do is I want to connect to the O on the right somehow. So let's do that. We can do the coordinate covalent bond. So remember what's going to happen. This is going to move over, and this is going to become the bond. But I'm still stuck on the top and the left. I still have a problem because this is not filled, and I don't have extra electrons. Okay? Now, side note, if I had SO3 negative 2, which you should know is sulfite, right? Polyatomic ion, sulfite, then you could have put an extra electron here, an extra electron here, and you'd be done. Okay? But we don't have sulfite. We actually have sulfur trioxide. So we cannot get any extra electrons. I'm going to try to erase this here. So we don't have an extra electron. Uh-oh, it's not letting me erase. All right, so what we're going to do is we're going to have to backtrack and do something else. This is unfortunate that this is not letting me erase here. Try it again. Okay, just going to have to cross it out. So cross this out, no extras, okay? What I'm going to do is I'm going to have to cross this out as well. It's a mess, sorry. Just won't let me erase. So I'm going to connect here to here, okay? Make a double bond on the left. Then I'm going to do another coordinate bond. So this electron right here is going to move over, and then this pair right here, which is on the bottom, but it's okay, it's all I got, is going to make the bond. Okay, so don't freak out. I know it's a mess, but we're going to just redraw it nicely. So here's the S. It's got an O on the right, an O on the top, and O on the left. So on the O on the right, I have a coordinate bond. This arrow, the green arrow, and then I have the 6 electrons right there. Then the O on the top, I have another arrow for a coordinate bond, and then I have 6 valence electrons for the O. And then the one on the left, I have a double bond, and then I have only 2 pairs of electrons on the O. So there you go. And that's the final answer. And now the last thing we're going to do is we're going to introduce what's called resonance. Resonance means you could draw the same thing in different ways without moving the atoms around. So if I keep left O, top O, right O in the same exact spots, I could have double bonded to the one on the left, or I could have double bonded to the one on the top, or I could have double bonded to the one on the right. So therefore I have a total of 3 resonance structures because I could draw this in 3 different ways. Okay, so switching around a double and a single counts for resonance. Okay, if you switch an arrow and a single, it wouldn't matter. Okay, so for instance, if you had an arrow here but a line here, that doesn't count as switching because they're both single bonds. So this has 3 resonance structures because you could draw it 3 different ways. This has no resonance because you can't do anything differently. You can't do anything except a triple. So this doesn't have any resonance structures, nor does this, nor does that. Okay, but this one does.